Thank you, President Albrecht and Dr. Wheeler and Regents for sponsoring this program. I recognize some familiar faces from Fred Provenza's talk last time, and you'll notice a couple of commonalities between my talk and Dr. Provenza's. One is that Fred started his talk by saying that it was about behavior. This talk is also going to be about behavior in a slightly different light. Two, Fred warned you that he was a very fast talker, and you may have already caught on that I too am a very fast talker, so if you need to slow me down, and I'll take a step back. So I want to talk to you about some research that we've been doing for about 10 years in our group on maladaptive behavior and its relationship to addictive behavior in humans. So people engage in all manner of maladaptive behavior patterns that are self-destructive, and when you look at them from the outside, and all of us know people who have engaged in these sorts of behaviors, some of us have done it ourselves, it just doesn't seem to make any sense from the outside. It seems completely irrational. Why would people continue to do these things that they know are harmful when everybody else says you should stop? Overeating is one example. This is a great place to talk about this. We have a wonderful free breakfast so you can eat as much as you'd like. All of us recognize we have to show some self-restraint here. Right? Gambling, risky sexual behavior, and I've spared you the gory picture over here on the other side for that one. And what I want to talk to you about is drug and alcohol abuse, because that's the one that our group focuses on primarily. Now, what I'm going to say to you really is applicable to all of these sorts of maladaptive behaviors, even minor things like speeding or watching too much television or drinking too much coffee or whatever your maladaptive sort of behavior or preference might be. And this behavior is costly, and we'll just talk about substance abuse here. And it's estimated that substance abuse costs the U.S. About $500 billion a year. About 181 billion of that is from illicit drugs. Move away from that mic. 168 billion from tobacco. These are just the economic costs, however. This doesn't capture the human costs associated with these problem behaviors. Just to get a feel for that, 400,000 people die in the U.S. per year from smoking cigarettes. Everybody knows cigarettes kill you, right? So why do people do this? Most smokers who smoke would like to stop. Why can't they? Alcoholism. Alcohol, 185 billion per year. Now, that's pretty heavy stuff, so let's lighten it up a little bit here. This is one of my favorite cartoons of all time. It's called The Miracle of Consciousness. And if you can't read this, what it says up here is, making the human the only animal that can be the master of its own destiny. And so here we have this guy eating his sandwich, and he says, why am I eating this stuff? It's terrible for me, but I can't stop. And the important thing to look at over here is we have our pigeons over here eating some grain off, and he has an empty bubble. Of course, he's eating the food and can't stop either, but his bubble is empty. I wonder why I keep going out with her. She's totally wrong with me, for me. And here we have our pigeons walking together. Their bubbles are empty, engaging in the same sorts of behavior. Oh no, I'm yelling at Wayne, and there's going to be trouble. Why am I losing my temper? And here we have one pigeon attacking another with, of course, an empty bubble. Again, the miracle of consciousness, right? Making humans the only animal that give us the control of our destiny, right? We all recognize these things in ourselves and others. So what's going on here? What are typical explanations for these sorts of things? Well, character flaw is up there, and we all have our character flaws, of course. Lack of willpower. We lose control of ourselves. People who suffer from substance abuse or gambling or overeating, we say they have a lack of willpower, and sometimes it's character flaw or it reflects poor judgment on their part. Now, as a psychologist and a scientist, for me, these are questions of brain and behavior. And so how can we use what we know about brain and behavior to understand this sort of human behavior a little better? And if you think about the roots of many human problems, constantly human problems, not just the ones I talk about, a lot of them are rooted in human behavior. So I want to start with the story of Phineas Gage. Most of you have probably heard something about Phineas Gage. He was a 25-year-old railroad worker. They were working near Cavendish, Vermont. He was a foreman. His job was to tamp holes that had gunpowder in them for blasting. And so they drill a hole, fill it with gunpowder, and you tamp it with this 13-pound tamping iron. Gage tamped, caught a spark, it exploded, and sent the tamping iron through the front of his head. interestingly, rumors are that he spoke within minutes and he walked away from this with assistance. Now, here's what Dr. John Harlow, the attending physician, said years later after reports about changes in Gage's behavior from his friends and family was the equilibrium or balance between his intellectual faculties and his animal propensities seems to have been destroyed as a result of this accident. Now, note where that tamping wire went, right through the front of his head, right here. Now, before the injury, he was described as being well-balanced, a well-balanced mind. He was a smart businessman. He was persistent. He executed his plans. Afterwards, he was impatient of restraint when it conflicts with his desires. Future plans were abandoned almost immediately. Now, I'm the father of a 2-year-old, and this sounds like my 2-year-old to me. Now, I have also heard that this could be true of teenagers. If you have teenagers, that this sounds like them as well. And it turns out that's really no accident. That front part of the brain is the last part to finish developing, in fact, well into your 20s. It's also no accident that insurance rates go down at 25, and that's because this part of the brain, where these things are seated, keeps developing into your 20s. Okay, so his mind was radically changed. He was no longer Gage. He wasn't the same man. What this started to reveal to scientists is that character, judgment, willpower, all of those things have their basis in brain functioning, specifically in this frontal part of the brain. So I want to talk about that frontal part of the brain for a minute. It's generally considered, it's up here, if you can see this. The seat of executive functioning, this is where the U of you is. Planning, decision-making, and importantly, it stops you from engaging in behavior that might otherwise be automatic. You may have enjoyed the delicious sausage and want to run up and grab 5 more of them. This is the reason that you don't, right? Now, the brain is a complicated thing, but the part that's going to be important for us here today is the dopamine reward circuit, which is down here more in the middle of the brain, which is mediates pleasure, compulsion. It's the seat of reward learning. And so the rewarding effects of eating that sausage are happening there. They're feeding up to the front, and the front is feeding back, helping you make correct decisions about what to do here. Now, I'm going to talk about this reward learning first, and we'll work our way back to this executive functioning piece toward the end. So reward learning, which is really the specialty of our laboratory. I'm going to start with Pavlovian conditioning. Fred also talked about this a bit. This is just learning that some things in the environment, some stimuli, predict other stimuli in the environment. So the classic example is Pavlov's dog. So we have our dog here, we give him a piece of food, and he salivates. If we take a bell and we present that before we give the dog the food, do that over and over again, eventually what's going to happen when we present the bell? It's going to salivate. So this thing that didn't really mean anything to the dog has come to produce salivation as a result of this Pavlovian conditioning. Okay, now, this is also referred to as associative learning, learning what goes with what. It's also deeply involved in emotion and emotional learning. These things produce, you learn to fear objects that are predictive of bad things happening. This is the source of things like anxiety disorders. People are involved in car crashes. They can't stand to get in a car anymore as a result. This is the kind of learning that underlies that. For our purposes, we're more interested in these other things. They generate excitement, like our friend over here, who you may see when you open the refrigerator at your house, right? The refrigerator doesn't mean anything to the dog until after the food comes out of it a few times, and then you get this. Arousal, motivation. Spot here is really willing to sit and shake your hand after the refrigerator comes open and you have the meat in your hand, right? Okay. Now, the other side of reward learning, which is really important for us here, is operant conditioning. And this is learning that your behavior has consequences. And this was really popularized by B.F. Skinner. It was earlier discovered by Thorndike. And for example here, if you have a rat, this is a typical arrangement with a rat here. He's in a little chamber. He can press a lever. He's hungry. It produces a food pellet. The animal rapidly learns to press the lever, and the food pellet comes. And the behavior goes up as a result of that. We call those reinforcers. When bad things happen, the behavior tends to go down. We call those punishers. And this is the seat. Now, this just doesn't happen with rats in little chambers here. This is what we've known for over 100 years, that this also has a large impact on human behavior. You're eating your breakfast this morning is operant behavior. You're coming to this meeting as opposed to doing something else is operant behavior. You make decisions, you engage in behavior, there are consequences as a result. We generate might refer to this as goal-directed behavior or voluntary behavior. It's deeply the source of choice and decision-making. So for my example, take our rat here. He can press the lever and get a small reward right now, or he can press a different lever and get a bigger reward if he waits a little longer. Okay? Now, these two types of conditioning interact all the time. So stimuli that predict reinforcers or rewards, they come to modulate behavior. They serve as signals. They tell you what to do. So so take our rat in the chamber there. When the light's on and he presses the lever, he gets a food pellet. When the light is off, he presses the lever, nothing happens. What happens as a result of this? The rat learns to press the lever when the light is on, not to press it when the light is off. You may recognize some of these over here. The door on the store says, come in, we're open. You learn to go in then and not when it says closed. It's very disappointing when it says open and it's not, right? These are well-learned behaviors. They come to modulate your behavior. These cues are important for doing that. Now, they also come to motivate behavior, and that's why I have these interstate signs here. Not only do they tell you where the food is, but even if you weren't particularly hungry, you might start to be after seeing them, and you may be motivated to get off at that exit. They also, we know, tend to produce automatic and persistent behavior. So you learn these rewards, the cues, you start to engage in these things pretty automatically, like driving your car. You keep it between the lines. Often you're thinking about other things, talking to people, listening to the radio. It starts to become automatic once it's well trained in response to the cues. And they attract and keep attention. Especially if you're hungry, those road signs become very important, and you look at them a lot. So here, the far side always has a relevant cartoon for any scientist, and so here's ours. It says, Windows Zerkowitz, slave to the waffle light. And there he is. He's waiting for the light to come on and for the waffle to be ready. He's there looking at it, ready to go. And it looks like he eats a few of those waffles. Now, back to addiction. So it turns out drug taking is operant behavior, and we've known this for a very long time. This is a revolution in our understanding of addiction and drug taking. Drugs reinforce behavior that produces them. Lighting the cigarette is reinforced by the delivery of nicotine. Drinking a beer is reinforced by the alcohol delivered. Going to the convenience store and buying cigarettes is reinforced by having access to the cigarettes. And stimuli that predict drugs become conditioned cues just like all those other things we just talked about. And they have similar sorts of effects. It turns out that that sort of reward learning is critical in habitual behavior, like I said, automatic sorts of behavior and addiction. And there's an awful lot for us to learn about this still, and that's what we're doing. So what is addiction? A pretty well accepted definition. This is from a group of physicians that studies addictive behavior. It's a chronic brain behavior disease. It's a disease of the brain reward, motivation, and memory and related circuitry, that reward circuitry and its relationship to the frontal circuits. Now, here's the thing. The same processes underlie natural reward learning. So the reward learning that's happening with you in your breakfast, or the reward learning that happens when you interact with your smiling 2-year-old. The pleasure that you get from that and the rewards associated with that and the learning about that are mediated by exactly the same parts of your brain that mediate the effects of drugs. Often we talk about drugs hijacking this reward system. They work on the same neurochemicals that mediate these natural rewards, and the drugs hijack it. It's characterized by compulsive or habitual seeking, a loss of control. You can't stop, despite people wanting to stop, and despite the fact that it's ruining their lives and having negative consequences, they can't stop. And people who are addicted tend to show strong reactivity to drug cues. Now, this is also true of obesity as well. Most of what I'm going to say to you, you can translate between obesity and addiction, drug addiction, pretty straightforwardly without many changes in this talk. So what about drug cues? They attract attention, they cause cravings and urges, and we know that they contribute to relapse. Even people who've stopped using drugs years ago are exposed to a cue, they may have an urge, and often they relapse. Smokers, if you haven't smoked for 5 or 10 years, you still may walk into a convenience store and see your brand of cigarettes behind the counter and still experience nicotine withdrawal and cravings and a desire to buy a pack of cigarettes. So animal lessons, where do those come in? Why would we use animals to study this sort of thing that seems sort of truly human to engage in these kinds of behaviors? Well, it turns out that the processes are similar across species. It's a lot like using animals to study diabetes, for example, or cancer. Are they exactly the same? Absolutely not, but their brains are similar enough, and their behavior is controlled in similar enough ways that we can learn a lot about these processes with animals, just like with cancer. We can control the environment and experiences, because remember, this learning aspect is a critical part of it. And we can more easily study the neurobiology and genetics of this in animals. Now, a standard way to do this, which is important for our purposes, is the drug self-administration procedure. So how do you study addiction in animals? And so what we have here is a rat. He's in the chamber, except this time, rather than pressing a lever and getting a little piece of food, he presses it in, he gets a small infusion of drug, for example, cocaine. In our lab, we often use alcohol, so they are just drinking out of a cup, but we do use other drugs of abuse as well. Drugs that humans abuse function as reinforcers, as rewards for animals in these preparations because of that shared biology. In fact, this is how we test the abuse liability of new drugs. Most of the drugs you've ever taken have gone through this preparation to see if they function as a reinforcer for animals, and if they do, they're going to need to be controlled because they're probably going to be abused by humans. In fact, it's part of the definition of an addictive drug is that it serves as a reinforcer in this preparation. This is from C. Everett Koop, the Surgeon General under President Reagan, when he was working to define nicotine as an addictive drug. This is what he said about it. The drug is reinforcing. That is, the pharmacologic activity of the drug is sufficiently rewarding to maintain self-administration. This is how we define addictive drugs in part. So what do we do? First, this is Amy Odom, my partner in science and life. Our greatest collaboration is our two kids, but we collaborate on science as well, and she's here today too. What do we do? We study how natural reward processes might produce maladaptive behavior, especially substance abuse. How does reward learning contribute to this? And we use that self-administration procedure a lot that I just talked to you about. We really specialize in creating new procedures to study this sort of thing, to generate situations that map onto important aspects of the human condition. That's sort of our specialty, is developing new ones of these that we and others can use. For example, how do you study attention to drug cues in an animal? How do you study the impact of cues on persistence of drug seeking? And relapse, how do you study relapse in animals? So attending to drug cues, let's start there. So we've developed an animal model of attending to drug cues. Here's one for you, the bar sign there. If you drink, there's a cue. How do we study attending to those sorts of cues in animals? And really, here's how it works. We have an animal in there. They're working for the drug, like I just described to you, and they can also work for cues that tell them when the drug is available, and that's our measure of attending to it. Other folks have extended this to monkeys and attending to other drugs like cocaine and various sorts of opiates along the way. So what have we found using this preparation about attending to drug cues? Well, once you establish this sort of attending, it's very hard to get it to stop. Even after the animal stops looking for the drug, stops trying to take the drug, they still look for the cues. They still look at the cues. And we're trying to model that aspect of you going into the convenience store, you haven't smoked for 5 years, and there you are looking at the packs of cigarettes behind there. For some reason, it seems hard. Well, now we can model that sort of thing in the animal laboratory to start to understand the basis of that a little bit better. And this one was sort of surprising to us. We expected exactly the opposite result, is that rats attend to alcohol cues more when the alcohol content is low than when it's high. And this is relevant in Utah for 3-2 beer, for example. If you think about polygamy porter, when the alcohol content is low and you're drinking for alcohol, what do you need? You need more drinks. And so it turns out here that attending to the cues is useful for finding drinks. And so the attending is actually governed by how you use them to get to the drug. And most people who study conditioning and learning, including myself, would have expected the opposite result. If the drug is the reinforcer, you'd expect them to look more at it if they got more drug. But it turns out it's more of an economic sort of situation where they're using the cues to get to drug. So we're starting to think about the implications of that for understanding human attending in these sorts of situations as well. After rats attend to cues, the more they attend, the more they drink. If you can decrease their attending, you can decrease their drinking. and we've shown that to be true. The difficult part with humans is getting them to stop attending so much, although we have some ideas about how to approach that issue as well. So also, after they attend to a drink, it's really hard to get them to stop, and they'll pay more for a drink. So after you look at the queue, you see how much they'll pay for a drink. They pay more if they've looked at the queue. Now, of course, we don't give the rats wads of 20s here. If you do, they shred them in little pieces and make a nest out of it. The way that you study this in animals is you take that lever and you make them press more and more and more and more. You increase the cost associated with getting to the drug, and they have to press more and more and more to get there. And we use standard microeconomic demand curve theory to estimate elasticity of demand to see how much they're willing to pay. So what about relapse? What we found is that with both alcohol and cocaine cues, if you take more drug in a queue, it's very hard to get you to stop looking for drug in that queue. So the more you've experienced drug in those queues, the more you keep looking for drug in those queues later on. And there's some corresponding data from Johns Hopkins with human substance abusers in treatment. Frequency of drug use is a good predictor of how hard it is to keep them in treatment later on. We can now model that in the animal case here. And this is one of the things that we're probably best known for is that natural and drug rewards interact in slightly surprising ways. And although it's not too surprising if you remember that it's the same reward system here. So if you've gotten other sources of reinforcement in a queue with your drug, it turns out that your drug seeking and taking in that situation is stronger and harder to get rid of. And so here we have the hamburger example with your beer. It turns out that the hamburger contributes to your alcohol seeking inside there too. Now, another potent reinforcer for substance abusers are social interactions here. So at the bar, you're interacting with other people, you're getting those reinforcers. All of that contributes to the drug seeking itself. And they make you more likely to relapse in that context. So even if they compete with it, so if you have a hamburger there and you actually drink less beer, it doesn't matter. You still are more likely to relapse in that situation as a result of the combination of those. Now finally, we're trying to build a better model of relapse with animals. The existing models, basically they withhold the drug and the animal gives up eventually, and then you do something and they start looking for the drug again, and that's your model of relapse. Often what they do is you expose them to the drug, and this has really no validity in the outside world. It's like somebody ran up to you and injected you with drug, and now you've relapsed. It does have some predictive utility, but that's about all. Exposure to drug cues, this is important. So you take a cue and you represent that, and the animal starts working for drug again. They relapse. Or they experience some physical stress. We know stress is a critical component of substance abuse and relapse. But for us, we're thinking about this, human relapse is not usually produced by physical stress. It's usually produced by other sorts of stress or loss. So often when you lose non-drug reward, so here we have our couple fighting, you lose your job, you get divorced, we know in the human case that these things produce relapse or increases in drug seeking and taking as well. So we wanted to model that in animals. And so we've developed the first procedure to study relapse caused by loss of another reward, of a natural reward. So the animals have access to a natural reward, they lose it, and what you see here after our treatment here, they're not really taking much drug, and after you take away that, they still can't earn the drug here, so it goes away eventually too. But what you see is their seeking of the drug goes way up whenever they lose that natural reward. And so now we're starting to try to understand the neurobiology of this. We've started with dopamine, and we can show that we can block that sort of relapse by blocking dopamine D1 receptors as a place to start with cocaine as the drug of choice here. So we're going to be working on that a lot more. Okay, so just to recap the reward learning, don't get too excited. We still got to do that whole decision-making part, so bear with me. So to recap this piece, we're generating new ways to study how reward learning contributes to addiction, especially focusing on problematic attention and on novel models of relapse and persistence. Remember, if you remember nothing else from this talk, that these same processes underlie these things. The rewarding effects of that photograph are the same as the rewarding effects of taking cocaine. It's a matter of degree. They work in the same sorts of ways. Natural rewards contribute to persistence and relapse in the contexts, and losing them can produce an increase in drug seeking or relapse. So it's not really a problem of just drugs, it's a problem of the reward system. So turn your attention away from the drugs so much, more into that piece of the brain there, right? But, okay, wait a second. Most people, what about that decision-making system there, right? Most of us can say, oh, don't do that, right? Don't get up and have more sausage. Don't have another beer. Don't buy the cigarettes. And most people manage to not become addicted, even though most people try drugs or alcohol, drugs of some sort or alcohol, sometime in their lives. Most people don't become addicted. So why not? What's the difference? Of course, the reward system is only part of the problem here. We all have a reward system. So I want to talk a little bit about impulsive decision making, and this is a lot of work that Amy has done as well. So the procedure and theory were really developed in animal learning experiments, like I've talked to you, and they've been extended to the human condition like this. So you give people a choice between small, immediate, and larger delayed rewards, just like that first choice I presented to you. So over here, would you prefer $100 now or $100 in a week? That's a pretty easy decision, right? You take the $100 now. But now, what about $90 now or $100 in a week? Are you willing to wait a week for the extra $10? Probably. What if we get down to $30 now and $100 in a week? Most people would say, yeah, I'd wait, right? But if you're impatient or impulsive, you might say, look, I'll take the $10 now rather than waiting for a week for $100. I'll take the money right now, right? So you can get a measure of impulsivity here. And it turns out that people show normal variation in this sort of impulsivity. These are real data from, I give this to all my undergraduate classes. These are real undergraduates at Utah State University in my learning class. And look at the variation that they show. Now, these lines that go pretty straight across here are people who are very self-controlled. They're willing to wait forever to get that $100. This person, right here at the very bottom, this person said after a week or less, basically no money, I'll take basically no money now to avoid having to wait a week to get it. Okay? Those are big differences. And after you do this for a while, you can actually start to see some predictability. I can tell you that this person was indeed a cigarette smoker, and this is foreshadowing where we're going next with this. It turns out that this is really relevant for substance abuse because the negative consequences of taking a drug are usually delayed, right? You're not going to die of cancer. If you died of cancer the first puff you took on a cigarette, nobody would smoke, right? It's probabilistic. It's delayed. The rewarding effects of the drug are immediate, right? Now, substance abusers, it turns out, are hypersensitive to immediate rewards and tend to behave impulsively on these sorts of tasks. This is Greg Madden. This sort of started an entire area of study here. He showed with others that people who are addicted to opiates showed very impulsive decision-making on this sort of procedure. And I'm really happy to say that we've recruited Greg Madden to USU. He started about a month ago. He's come to join us in the psychology department, and that's him down there. So we're getting together an excellent team to study these sorts of issues. Okay, so delayed consequences don't have much of an impact on addicts' behavior. Now, it turns out this is also true with cocaine, or actually any drug you can think of except for marijuana, it turns out. But just about any other drug you can think about, they show steep discounting and impulsivity in these preparations. Cocaine, meth, alcoholics, smokers. Amy and Greg Madden published a really influential study on this a while back, showing that this is true of smokers as well. It's also associated with the severity of use. Casual drinkers are less impulsive than regular drinkers. Non-drinkers, even less so. Same with smokers. Light smokers, less impulsive than heavy smokers. It's associated with the age of first use. So you ask college kids, you give them this, you ask them when they first started taking drugs, how many times they've passed out, when did you first drink, when did you first smoke, and it's associated with their self-reported age of first use. Folks who are more impulsive on this task have taken drugs earlier. It also predicts relapse. Most women stop smoking when they're pregnant. Some of them relapse. You give them this series of questions while they're not smoking, you can predict which ones are most likely to relapse after they have the baby. It's similarly associated, this slide should look familiar because it's where we started. All these things, overeating, risky sex, gambling. It turns out that all of these sorts of patterns of behavior are associated with impulsive decision-making in this kind of task. What we know about the neurobiology of this is that showing self-control, we're back to Phineas Gage here, see him down in the bottom with his lesion produced by the tamping iron. From MRI studies, we know that self-control depends on this prefrontal cortex as well. And when people are making these decisions, when they behave impulsively, it turns out that you get more of sort of a lighting up in that reward-related area than in the frontal area here. So you can predict self-controlled and impulsive decisions based on the relative activation of those two areas. And as a base rate, addicts tend to show reduced activity in that frontal cortex. Also true of the morbidly obese. We can measure the same thing. This is going to tell you about the future of where we're headed with this. You can measure the same things in animals. We started with this before. Small reward now, large reward later. You can get those same exact curves. In fact, they were first gotten out of animals. And when you get them, we know that rats who behave more impulsively self-administer more drug. Genetics. There are differences across strains of rats. Some of them behave more impulsively, and those are the ones who take more drug. There are also environmental factors. Highly unpredictable environments tend to generate more impulsivity in these sorts of preparations. And with the animals, we can examine these sort of competing brain systems more thoroughly and relate them to reward learning and the interaction between that and judgment or decision making. So conclusions. Addiction is largely based on reward learning and decision-making processes, and these are processes that are conserved across species. These are shared across species. That's why there are animal lessons here. Right. Addiction is characterized by overreactivity to immediate rewards and to cues associated with them, and underactive prefrontal functioning, impaired decision-making, impulsivity. So what are the implications of this for treatment? I don't do treatment, but I can tell you this is a very good treatment here, contingency management. Focus on reward learning in treatment if you want to have effective treatment. In contingency management, they provide incentives for staying clean. So if you're a heroin addict, you might provide a urine to show that you haven't used it. You earn some incentives that are exchangeable for goods and services. That ramps up over time. You earn more and more money because it's harder and harder for people to stay clean for a period. And what you find is that you get really good compliance with these sorts of things, and it works really well. In fact, this is recommended by the Utah Department of Substance Abuse and Mental Health, although I don't think anybody's actually doing this in Utah because it's an evidence-based practice. But nobody that I know of is really doing this here. Here's some data up here. It says behavioral. This is people who are not using drugs in that week. And this is standard drug abuse counseling where you see you've lost everybody out here at 20 weeks. Nobody is really doing this anymore. And with this contingency management, you're maintaining, way out here at 24 weeks, people are still off. Now, the depressing part is that we start at 50% on week 1 with everybody. That tells you how much we have to learn. This is one of the most effective treatments, and it's pretty effective. At week 1, we start with 50% of the people not participating anymore. So there's an awful lot to learn about how to make this better, which is what we're trying to do. The other one that is closely related and sometimes used in combination is the community reinforcement approach. And this is where you teach people to identify those cues, so you make them conscious of these cues. You try to avoid these cues. You teach them how to deal with it when they're exposed to the cues. Find them non-drug sources of reinforcement. Teach them to go hiking. Get them a job, doing all those sorts of things. And enlist their family and friends to help keep them going so that you don't need someone providing treatment from outside all the time. Some people from within are helping to help them stay off of drugs and find other reinforcers. So finally, what you should walk away from here with is that behavioral brain functioning varies across individuals, right? This is what we call character, really, right? Seemingly irrational behavior is related to this sort of functioning. And it's a fundamental aspect of human nature to realize this about ourselves, that there are variations across people and ourselves at different times, that we have a tendency to behave in maladaptive ways. The good idea here is to focus on early assessment and intervention. Identify people who are most vulnerable relatively early. And Amy is working on this in part with really little kids to identify decision-making that happens impulsively. Use reward learning and decision-making based assessments to try to figure out who is actually at risk. And then focus your prevention on them. It turns out that most people don't need the prevention message as much as some do. Find the ones who need this message the most, who are most likely to have a problem, and target it to them. And then finally, just in general, try to aim for understanding and coping with our tendencies to behave this way as people. And so just for further reading here are some great pop science books. Mind Wide Open by Stephen Johnson. He talks a lot about these same sorts of issues. Descartes' Error by Antonio Damasio. And then I put that up there. That's Greg Madden's book, Impulsivity, published by APA. It's a bit more technical, but there's a lot of good information in there. So thanks. Yeah.
Doctor, you talk about relapse in humans is often signaled or precursed by loss.
Yeah.
Yet one of our standard things we do in the legal system or in treatment is that, well, we have to pull this person out of those social circumstances they were in, because of course that support system got them into this, and maybe we all put them all in jail. Aren't these just completely units of loss?
Yeah, there's no doubt, and the problem is when we put people back into those environments after their time in jail, they're probably very much the same as when they left them. And so definitely you have to focus on structuring their lives, and the best way to help them out is to get them out of those situations, because of course and smokers know this too, even not worrying about the judicial system. Smokers, you quit smoking, and of course smoking is associated with everything. How do you get rid of all of that? And that's why learning to cope with those cues and triggers, or redefine them, give them other functions, is the important part. Is this easy with a substance abuser who's been in prison? Absolutely not at all, which is where things like contingency management come in. They can work for incentives, and so we're sort of helping to provide a prosthetic environment that helps them stay, does that make sense? To help them stay clean, because maybe their natural environment isn't all that much help, and move people into more supportive environments.
Just as a follow-up, you watch Mad Men, how entertaining do you find it?
I don't watch it, actually. I've heard about it. It sounds very entertaining, but no, I don't. Yes.
And impulsive behaviors. But solving those three things, there's never a very clear-cut answer. In your research, have you found anything that will help to improve prefrontal cortex functioning, reduce impulsive behaviors, or increase dopamine levels?
In my work, not exactly. That hasn't been our function, but I can tell you some things that are relevant. And these are really tough problems, obviously. How do you get someone to use prefrontal cortex more so and behave less impulsively? Lots of people are interested in training this. We do have procedures that have been developed with animals that can take animals that are behaving really impulsively and have them behave somewhat less impulsively. So teaching them to delay gratification. So most of us do this with our children, right? They scream and say, "Give it to me immediately," and we say, wait a moment and behave yourself and get it, and then you gradually make those longer. And so most of us do this sort of naturally, and some people haven't had those sorts of support, so they haven't worked very well, but people are interested in generating clinical programs that work to do that specifically, and those things are really just getting underway. Another exciting one is, this is starting to happen at University of Arkansas and also in Israel, is that it turns out you can stimulate parts of the brain without any invasive procedures with transcranial magnetic stimulation. So it's sort of like an fMRI, except it's really high intensity magnetic stimulation, and you can activate parts of the brain with these things. And if you activate the frontal cortex here, you can actually get people to behave with more self-control in these sorts of tasks. Again, this is all just getting started. And so lots of folks are interested in combining that with training. So you sort of light up those parts of the brain for people and teach them to make choices in these ways with the goal toward training them to do these things. In terms of dopamine, of course, dopamine is the holy grail of magic bullets for solving the drug addiction problem. And lots of people have spent lots of time, we've spent billions of dollars trying to find a magic bullet that will solve this problem. The difficulty has always been, and will always remain, is that it's the key to all reward learning. And so once you start messing with it, you start messing with regular reward learning as well. There is some talk of using things like bupropion and various other drugs that, frankly, and methylphenidate, which actually function exactly like substances of abuse, but to use them as substitutes for the drug, say for cocaine, so that it's like using methadone for heroin addiction, whereas you're giving them a pill every day that lets them lead a normal life and not engage in all this drug-seeking behavior, and so there's a lot of interest in using those sorts of treatments too for treating at least stimulant abuse. I think I got all those pieces, I hope. Yeah.
You mentioned marijuana as being not a category.
Yeah.
I'm just wondering what you have found with respect to that. Or have you studied that?
We've done very little work with cannabinoids, and it didn't work out when we did. But people are really interested in that these days as a result of changing marijuana laws. And it's just, marijuana sticks out as an example here with this decision-making stuff in that it's pretty much the only one that chronic users do not show this intense, steep discounting. And so it's notable for that reason, but we haven't really done anything with it. Yes?
We've been hearing about an addictive gene.
Yep.
15 to 20% of the population supposedly has. That if you use, you are hooked, and if you don't have the gene, supposedly you can break away. What have you found?
We haven't done anything with genetics as of yet in our group. I can tell you what little bit I know about that. And anytime you hear somebody talk about the gene for some human behavior like that, you should have a healthy skepticism about that. There are lots of candidate genes that are involved in a susceptibility to substance abuse. They do tend to focus on the dopamine sorts of receptors, dopamine transporter genes. There's some stuff in the noradrenergic system that's also relevant. A lot of that reward learning system is often called the mesocorticolimbic dopamine system. And so that's why genes for dopamine coding, production of dopamine, reacting to dopamine are really important, because that's connection between the reward learning center and those judgment centers is driven largely by dopamine. And so a lot of attention has been there. There's no doubt that people are differentially susceptible, and that's the sort of stuff that we're trying to find out about.
Can some animals move away where others can't?
Yes, absolutely. And you can predict which ones if you give them a series of choices. If you take the ones who are most impulsive, put them over there, you can see that they take more drugs, and it varies by strain as well. And eventually we will get to the point where you can call up a lab and say, send me a rat without this gene and they'll be an addict. We're not to that point yet. We're pretty darn close with mice, but so we're working in that direction. But it's not going to be a single gene. There's a lot of them involved.
My impulse at this time is to let Dr. Shahan continue, but my better decision making is that we ought to wrap this up to let some of you who need to go. But I think Tim will be able to stay around.
Yes.
If you have individual questions, feel free to come up and talk to him for a minute. Thank you very much for your presentation.
Thanks.